Professor S.S. Roy. Dr. Shibendu Shekhar Roy received B and M.Tech degree in Mechanical Engineering from NIT Durgapur. He also holds a PhD from IIT Kharagpur. He is currently working as a professor at the Department of Mechanical Engineering and Associate Dean, Alumni Affairs and Outreach at the National Institute of Technology, Durgapur. Professor Roy has published more than 70 papers in national and international journals, as well as 4 book chapters, and has filed a number of patents in the area of product development. He has co-authored 2 books on legged robots. He has completed a number of DST and DRDO sponsored research projects. His current research interests include modeling and simulating legged robots, soft robotics, rehabilitation robotics, additive manufacturing, and 3D printing on macro and micro scales. And sir also one of my best friend in IIT Kharagpur whenever we have done our PhD work. And thank you, sir, for within very short time, sir, accepting our invitation. Sir, now we can start, sir.
Okay, very good morning to all of you. And first of all, I like to convey my sincere thanks to Professor Kamal Pal and his team to invite me in this particular seminar, and it is my proud privilege to share some of my knowledge in this particular area in front of you. So now I like to share my slide. Just a minute. So is it visible?
Yes, sir. Now it's visible.
So I like to talk upon that role of additive manufacturing technologies in sustainable and digital manufacturing in the area of Industry 4.0. So as you know that the theme of your seminar is the sustainable and digital manufacturing towards Industry 4.0. So I structured my talk in this line, though I already know the Professor S.K. Pal, he is also my teacher. So he already covered the Industry 4.0, what it is and why it is required and what are the challenges in Industry 4.0. I just recapitulated that particular part, and followed by what is sustainable manufacturing, what are the features for the sustainable manufacturing should have. Then I like to talk about the digital manufacturing, that also covered by Mr. Mukesh in yesterday's afternoon session. And my focus is on the additive manufacturing, is in what's its role in the era of in the arena of substantial sustainable manufacturing as well as the digital manufacturing. We like to talk about that what are the technologies are, and more focus I like to give that some case studies and the research opportunities in this particular area. So if you see the Indian context, there are the many industrial sector where industry is scattered. So it's starting from your automobile, your heavy machinery development, power generation. There are the different customers product manufacturing. So each and every sector, as you know, the objective is, even after the post-COVID situation, it will be more prominent to develop our own product. That means we have to design and develop our own product. And as you see, any product development cycle or product life cycle starts with the identification of the needs. Needs might come from the manufacturer's end, or it may be from the customer's end. And once you identify the needs, then the steps you can follow that you will collect the relevant information from the literature survey, from the market survey, and have to carry out the techno-economical feasibility study. Once it is over, then we have to define our problem, we have to frame out our specification, and obviously the cost will be the factors. Whenever you like to develop any product, our objective is to develop the product of affordable cost, keeping in mind that we product designers, mechanical or electronics design, electronics engineering discipline, or any other discipline, we have to conceptualize the design, and then we like to carry out the modeling simulation, then engineering analysis, followed by the design optimization, evaluation, and it is iterative in nature. And then design documentation. Once the design is over, then we have to go for the planning for the manufacturing. Planning may be process planning, it's a capacity planning, manpower planning, material planning, and another important in the last 20-30 years is the tool design. So all these things had been carried out. After that, we'll go for the actual manufacturing. Once it has been manufactured, then you have to go for testing, quality control, and the packaging, shipping, sales service, and after sale service. So this, if in the nutshell, is the product life cycle or product development cycle. Now here I like to emphasize on that each and every activity there is a involvement of man, machine, and material. As there is a involvement of the man, machine, and material, and ultimately there is a involvement of the cost, whether it is the man or manpower cost, machine cost, and material cost. And also there is a time for each and every activity. There is a requirement of the time. So the two critical factors, that is the time as well as the cost, though it is sometimes interrelated. Now if you see the any product development organization, they are facing some challenges. Even pre-COVID situation as well as the post-COVID situation, both case the challenges are we have to develop our product with the shortest possible time, with the lowest possible cost, but keeping quality as high as possible. It should be competitive in quality point of view. So in order to sustain in the global competition, the new product can successfully enter if you can complete the above mentioned cycle, product development cycle, where I mentioned man, machine, and material involved. If you can complete that particular cycle in the shortest possible time and the lowest possible cost, the product development cost. So, and if you can maintain high product quality and reliability, then you can sustain in this competitive world. So that is why requirement is your production unit should be most economic, most productive, and improve quality, because productivity leads to growth, growth leads to profitability, and profitability leads to the survival in the market. So there are the main three factors that you have to develop your product with the shortest possible time. That means time involvement should be as minimum as possible, and your cost of the development, because ultimately the development cost will be distributed over the product cost. So that is why cost should be as low as possible, but without sacrificing the quality. So in order to cope with this requirement, one solution is to use as many automation as possible. So Professor Escapal also mentioned that use as many automation as possible. Then that such automation is extensively used for the last 30-40 years in the design activities using the CAD, but its capabilities of the CAD and increasing day by day. So these are the one automation tools in the area of design activity. Similarly, the automation in manufacturing activity is the CAD CAM tools. Again, last 30 years, people are using these particular tools. Similarly, automation in the product management activities. So these are the tools for the automation in product management activities. But it may be the last 25 years, not before the last 5 years, the industry are used to use this automation tools separately. But now it needs the integration. So Industry 4.0 is, in crude way you can say, it is the current trends of automation in manufacturing, or the for that more specifically for the factory automation. So automation tools people are knowing for the last 30 years, but integration of the among these is very important. And that is why the current trends of automation in manufacturing to make the factory much smarter than previous, the concept has been coined, that is Industry 4.0. Now, as Professor Paul mentioned, Industry 4.0, if you see its industrial revolution, it starts with Industry 1.0, Industry 2.0, Industry 3.0, and so on. I like to show you the brief history of Industry 4.0. Before that, I like to show you for the in the current context what the Industry 4.0 is doing and what are the different technologies used in the Industry 4.0. So I'd like to show you this video. So please bear with me. Please listen carefully. Here, the machine and product communicate with each other in the modern industry. So this is the history of industrial revolution. So this way the industry is moving. And as you know, the term industry 4.0 is coined in German government in the year 2011. And it is also known in USA as a name of a smart factory. So German term, the trends of automation and the data exchange in manufacturing, and the same thing is coined in USA, that in a smart factory that includes cyber physical system in IoT and the cloud computing to make the factories more smarter than previous. So I would like to show you another views of that. So basically now it is data driven manufacturing environment. So this is your, in short, you can say industry 4.0. So it is combination of intelligent machinery, production and processes in a system that form a sophisticated interconnected network. In addition, it emphasized the idea of coherence, digitization, and linkage of all productive units in an economic way, and creating the real world visualization in a large information system. And that is why through this concept, it has ability to collect information, it can share the information, and it has ability to use information to take better decision and to make productive. So this is the main theme for the industry 4.0, to make factories much more smarter, and that is why it is also called the smart factory. So the elements that you already know, that these are the element like your that big data, analytic, cloud computing, autonomous robot, augmented reality. Here the sensor technology is very useful. Sensors, actuators, So without this, it's very difficult to implement in the hardware level. So system integration, the industrial IoT, and obviously the in the manufacturing core manufacturing sector, there one of the disruptive technology like additive manufacturing is these are the technologies which are transforming the industrial production in the arena of industry 4.0. So these are the different components that already Professor Paul has been mentioned. I like to skip the individual component level. So here we like to emphasize on that two things. One is the use of artificial intelligence and machine learning algorithm and use for the autonomous robotics. And we have to design the much more efficient or smarter robot to cater the industrial needs. And that is why artificial intelligence and the sensor technology and the machine learning will be very useful technologies in respect of industry 4.0. And if you see the different technologies in industry 4.0, and though it is not restricted within a particular discipline, but still we have, I like to show you these are the discipline are involved in this particular technology, where mechanical engineering, production engineering have a prominent role. So in this particular lecture, I like to more focus on the your additive manufacturing, this particular part I like to focus where most of the discipline are involved. Uh, so there is another concept is the internet robotic things. It is the concept where intelligent device or robot can monitors. There is a data fusion is required from the varieties of source, and ultimately the machine will talk with the other machine to solve the problem. So five basic principle in industry 4.0 are the interconnection, information transparency, technical assistance, and the decentralized decision. So why industry 4.0? Because as you know, it's shorter the lead time or the product life cycle time, the cost effective and flexible. And the benefit I already mentioned, it's improved productivity, it enhance the customization. So mass customization is possible with this concept, improve worker safety and output, and you can access data across the supply chain for the better decision making. So major innovation in the digital technology for automation provides significant benefit for the manufacturing sector and utility of the consumers. So and that's why not only the developed country that factory like they like to equip with industry 4.0 concept in Indian industry also trying to implement that one, and it will be more important in the post COVID situation. So as I mentioned, the faster production, some of the case studies I like to show here, the speed up the manufacturing process, and it's a better quality, and it's the downtime, decrease the downtime 50%. This is some case study has been shown. So improved decision making possible because you can access data in any time from anywhere. So, and what are the challenges? So still there are a lot of research has to be carried out to solve these technological challenges like the communication, reliability, cyber security, and machine intelligence. Still, it is the beginning at the very niche stage. So there are a lot of maturity is required and handling the big data, but it has also social impact because of that general reluctance to change by the stakeholders, lack of adequate skill set. So these are the, and people are thinking for the it will create unemployment, but it's not true. That Professor Pal already explained in the yesterday's lecture. So in short, industrial production system are being transformed due to the high level of digitization, which leads to an intelligent, connected, and the decentralized production. And the core idea of Industry 4.0 is to use the emerging technologies that we have mentioned in the 9 technologies in a way that business and engineering processes are deeply integrated, making production operate in a flexible manner, efficient manner, and sustainable way with constantly high quality product with a low cost. Now, sustainable manufacturing is important. So it's basically defined as the integration of the processes and the systems capable to produce high quality products and services using less or more sustainable resources like energy, material, being safer for the employees, customers, and surrounding peoples, and being able to mitigate environmental and social impact through its whole life cycle. So if you compare with the simple manufacturing with the sustainable manufacturing, a sustainable manufacturing, the creation of manufactured product that use the processes that are non-polluting, it conserves energy and the natural resources, and are economically sound and safe for the employees, communities, and the consumers. So that's the main difference of the general manufacturing we are using and the manufacturing which we call as a sustainable manufacturing. It should have this sort of feature. So sustainable manufacturing processes are those which generate minimum quantity of wastages, demonstrating the improved environmental performance and energy efficiency while providing the operational safety and the personal health. So these are the main feature of which a manufacturing process should have, so that you can call that as a sustainable manufacturing. So sustainable manufacturing is the branch of sustainability that deals with economical, environmental, and social objective of the manufacturing activity that I like to show you here. The three pillars of sustainability is your environment aspect, it has the economy, and it should have a societal aspect. So these are the some the in different aspect we have already mentioned. That environment aspect point of view, you use less energy, it consume less natural resources to develop a product, and it should have a waste should be minimum, emission should be minimum from the environment point of view. Economic point of view also, it should be viable, and also the societal. So it's because there should be a safety for the employees, safety for the common people, it should respect the human rights and so on. So if you can any manufacturing process have this sort of aspect, or comply with this sort of aspect, then we can call that is sustainable in long run. So sustainable manufacturing, if you see that the 6R of a sustainable manufacturing, if you see the timeline, the sustainable manufacturing has a promising, and it's a sharp some innovation, and 6R in or innovative element which is defined by 6R in a sustainable manufacturing. It should be remanufactured, redesign, recover, recycle, reuse, and reduce the wastage and others. So that is, these 6R is very important in respect of the a manufacturing process is sustainable, because I already mentioned sustainable manufacturing is the creation of the manufactured product through economically sound processes that minimize the negative environmental impact while conserving the energy and the natural resources. So also the sustainable manufacturing enhances the safety of the employee, community, and also the product operator safety. So benefit you will get, there is a reduction in the cost by improving productivity, flexibility, and resource efficiency. There is a reduction of the wastage, energy consumption, and overproduction. So that I will tell you with example afterward. These are the main benefits of the sustainable manufacturing, along with the better brand reputation, market access, less labor turnover, and so on. So the key features that I already mentioned, through this you can control the pollution, cleaner production is possible, it should be eco-friendly, it should be life cycle. Also nowadays it is become shorter, closed loop production and industrial ecological balance should be there. So that already I mentioned that 6R. So this is the another views of that: redesign, remanufacturing, recover, reuse, and recycle. So these are the things that in nutshell I just explained. It should be energy efficient. That means energy consumption or power consumption should be less. Waste will be minimum, and the operational safety will be there. Personal health caring, health. It should not be health hazard. It should be environment friendly, and obviously the manufacturing cost should be as low as possible. Then only you call that manufacturing process is sustainable. So this is another view that I already mentioned. It's the minimum cost, minimum emission, and the optimal use of the natural resources like in energy, material, and other sources, including the labor. So if you can get this feature for any manufacturing process, then you can consider that as a of sustainable manufacturing. So there is a links between the industry 4.0 and sustainable manufacturing, because digitization and sustainability are the very theme across in all parts of the production chain. So both approaches present the practices government such as design for manufacturing, remanufacturing, recycling, applied to the life cycle management, reverse logistic for the circular economy, lean and green management for the resource efficiency, sustainable design reducing the risks of the worker or the consumer, so eliminating the use of toxic part in the product and production processes. Now in nutshell we just get the sustainable manufacturing in industry 4.0. These are the technological pillar that I already mentioned. So these are the scope of sustainable manufacturing. And if you see the industry 4.0 and the sustainable manufacturing, so these are the aspect has to be considered, and these are the dynamic model for the your sustainability. Now come to the next important keyword, the digital manufacturing. So digital manufacturing is nothing but your integrated approach that is centered around the application of digital system or computer system to manufacturing services and processes. So digital manufacturing technologies, it is started long back to the like product lifecycle management (PLM) tools, your different intelligent algorithm for making a factory smarter. So it is the technologies linked systems and the process across all area of production to create an integrated approach to the manufacturing, from design to production on the way of servicing of the final product. So digital manufacturing offer incorporate the optimization capabilities to reduce the time, to reduce the cost and improve the efficiency of the most of the processes. And there are the many different tooling process that digital manufacturing utilizes. So, however, every digital manufacturing process involves the use of computerized numerical control machine tools, that concept. And this technology crucial in the digital manufacturing, as it is not only enables the mass production, mass customization and flexibility also. So, but it also provide links between the CAD model and the production. There are the two primary categories of CNC system is used. One is in subtractive process, CNC turning, CNC milling, CNC drilling, and also CNC based different non-traditional machining. But another use of that is the additive manufacturing. So major strides in the additive manufacturing have came about recently and are at the forefront of the digital manufacturing. And these processes allow machine to address every elements of a part, no matter how complex its geometry. So that is why the technology, the ECNC is also used in the area of additive manufacturing, and this is nowadays considered as a disruptive technology in the area of mechanical manufacturing. So in digital manufacturing, basically it's a broad area. So here we like to focus on mainly the particular manufacturing processes. So one such manufacturing processes is the additive manufacturing process of 3D printing, which is one technological pillar of industry 4.0, and as well as the digital manufacturing. Now we have to see whether it will be sustainable or not. So before that, we like to give some intro, some of the additive manufacturing technologies which is nowadays available in the market, and after that we have to justify whether it will be sustainable or not. So additive manufacturing is also known as nickname, you can say the 3D printing. It is the post industrial revolution. But once upon a time, it was a dream for design and manufacturing technologies to develop such a technology which has a potential of directly converting the CAD data into the real object. And that is such a technology which provide the bridge from the product conceptualization to product realization in a reasonably faster manner. But and that means the rapid creation of the physical model to reduce the product development cycle. Now it is in reality in the name of additive manufacturing. And additive manufacturing is the process of joining the materials to create the object from the 3D CAD model data, and usually layer upon layer. So layer after layer material is adding. That is why it is opposed to the subtractive manufacturing methodologies. So the additive manufacturing process is very close to our nature. The way the nature has manufactured many things, if you can see in the bank of river or the bank river, you can see that the soil is depositing layer after layer, and after adding the years after years, the layer, the soil layer is depositing, and after a few years you might see this type of island kind of things. So the same principle is used in mechanical manufacturing by this additive manufacturing process. Similarly, in the nature, the plant, the animal has been created by adding material. It may not be the layer by layer, but by adding material, not by subtracting the material. So if you like, as you know, that principle of additive manufacturing is very simple. If you see this puzzle or cardboard puzzle kind of thing, right hand side figure, you just see if you like to develop this solid object of sculptured subject, sculptured model, then what you can do, this can be manufactured by subtractive manufacturing process using the CNC. Or if you like to do in this way, that you consider this particular 3D is consist of a number of 2D layers. So each layer, you just see the cardboard has been cut according to each layer cross section and add one after another by means of a glue, and you will get this one. The same simple principle is used in the additive manufacturing. First, you have to develop the CAD model of that object which you like to manufacture. Once your CAD model is over, then you slice it. The slicing means you're converting the CAD 3D model into the 2D geometry, a series of 2D geometry. And slicing is always taking place in horizontal plane, and it is the intersection between the solid and the plane. It will be again a cross section. That cross sectional geometry and dimension is stored into the CAD database because it is already there during your CAD modeling. So that means you are converting the 3D CAD model into number of 2D geometries. So that is slicing. Now, based on that, each cross-sectional information, you add material one after another. Now, how you will add material? For that, there are the 7 methodologies. But by adding material layer after layer, you will get the solid object. So this is the fundamental principles in the additive manufacturing. So if you see the general steps, so first you have to develop the 3D CAD model of the object which you like to manufacture. Then you have to save that particular file in the neutral file format, that is STL format, stereolithography format, STL format. You have to save it. Then you have to generate that support structure, some manufacturing process in overhang structure. the overhang structure like cantilever type of structure, from the bottom you have to give some support. For example, in case of the water tank, if you like to manufacture that, this is it is a cantilever, it is some hanging portion is there, you have to support of the different structure using bamboo, you have to give some support structure. In even also in a roof casting also you have to give support structure. Similarly here also overhang structure you have to give support, and that is why that CAD model of the support has to be generated. Then slicing. And slicing is always taking place horizontal plane, and that is why your part has to be oriented properly, or a more optimized way you have to orient so that wastage will be less. Wastage should be less, so that is why part orientation is very important. And it is digital level. Digital level part orientation is very important because slicing is always taking place in horizontal plane. So once you're sliced, that means you're converting your 3D object into the number of 2D geometries. And that is pre-processing. Now that number of 2D geometrical information which is stored into the CAD software that has been imported by the machine, the additive manufacturing machine, and material, depending on the methodology used, the layer after layer, the material will be added. And once it is over, the topmost layer will come, then you have to take it out, that particular component, 3D printed component, and then some post operation is required, it depending on the which particular methodology is used. That just I will explain this next slide, that it might be some post curing some cases post work finishing is required, and ultimately you will, after post processing you will get a product which may be used for the component for the prototype, or many cases it is the pattern for the complex component. But nowadays that limitation is not there. For few cases you can use it as a functional part also. But one thing keep in mind, when your geometry is complex, product geometry is complex, that time you will get its benefit. If your product geometry is relatively simple and mass production is required, then better to go for the traditional manufacturing process. But if it is a customized product is required or mass customization is required, and if your geometry is complex, then that time you can get the efficiency of the additive manufacturing process. Now additive manufacturing is also known as its nickname 3D printing, though 3D printing is coined by MIT in their product, but nowadays we loosely were talking all the additive manufacturing process we call as a 3D printing. Now if you compare with the 2D printing with the 3D printing, nowadays also 4D printing is also there, 4D printing. But here I like to compare about with respect to 2D printing and 3D printing. You see, in 2D printing also you have to develop the digital document either in Microsoft Word or Paint or any PPT, anything in MS Office. You prepare the digital model, then you have to feed into the printer. Now, if you see the working principle of the printer from the mechanical engineering point of view, it's just like see the motion. Let us say this is the inkjet printing system. Let us say it is inkjet printing system. Now in inkjet printing system, the print head is there. Print head consists of few thousands of tiny nozzle, or the very your micro level nozzle is there. From there, even nano level, from there that your ink will be deposited. Very fine particle of the ink will be deposited over the paper. Now if you see, according to your 2D graphics information, you have to deposit the ink, and in order to do that one you need XY movement. Now if you see the paper movement, paper straight line movement, if it is the X direction movement, then Y direction movement has given to the print head. The nozzle will move in a perpendicular to the paper movement direction. That means if paper will move along X direction, then your print head will move or the Y direction to deposit the ink according to the graphics information. So that means through XY motion, one layer of ink will be deposited over the paper, and you will get the 2D print. Now in case of 3D printing, instead of the 2D graphics, you have to develop your CAD model of your 3D product. So that geometry you have to, or the geometrical modeling you have to use. You have to develop 3D CAD model of the product. For example, here it showed me the gear. Now you can save into .html format, then slice it. That means converting 3D into 2D. Next, you feed that information to the printer, and if you see the in printer, there is a platform over which the material will be deposited. Say same over the platform, material will be deposited. Now, as you have converted the 3D object into number of 2D, now what happens at a particular platform, at a particular position, you have to deposit material, and in order to deposit material, XY movement is required. Let us assume XY movement has been given to the print head in this case, from where the material is jetting. Now, print head has given XY movement. Many combination is possible, but for the time being, we just assume that the print head has given XY movement. Now, by this XY movement, it will deposit the material according to the first cross-sectional information. That means depositing the material in 2D plane. Once the first layer is over, the platform is lowered down equal to 1 layer thickness. That means intermittent z direction motion perpendicular to xy, z direction motion of the platform is required. And once it will lower down by 1 layer thickness, next according to the second layer cross-sectional information, it will deposit the material, and this process will continue till the topmost layer will come. So that means it has a 3 motion, x, y, and intermittent z motion. So from the mechanical engineering point of view, in 3D printer have 3 motion to develop a particular product. Now, if you see the classification of the additive manufacturing process based on the initial form or initial state of raw material, which is the relatively old classification proposed by F.A. Chua, and according to him, the aim system has been classified into 3 groups. And that time, when this classification has been taken place, that time that additive manufacturing process is called as a rapid prototyping tools, rapid prototyping methodologies. But that name has been changed to the additive manufacturing. And based on the initial state of raw material, it has been classified into 3 groups. First, the liquid-based additive manufacturing process, and these are the commercially available product like SLA, stereolithography apparatus, SGC, the solid ground curing, SCS, solid creation system, SOUP, the solid object ultraviolet laser plotter. These are the liquid-based additive manufacturing process. Photocurable resin may be used, and it has been cured under the say UV ray. So next category is the solid-based additive manufacturing system. So here your initial state of material either in a thin sheet metal or somewhat semi-solid. Input is a solid filament, or it convert into semi-solid and it will deposit. So that the LOM, the laminated object manufacturing, it is based on the sheet metal, FDM, fused deposition modeling. It's the filament based. Similarly, the metal jetting modeling and SAHP. But most promising one, I can say that the powder-based additive manufacturing system. So the initial state of material is the powder, and powder has to be added here, or it has to be added either by glue or by laser based heating. So one is the cold powder based additive manufacturing when you use the glue. Another is the hot powder based additive manufacturing process when you use the laser. So one of the oldest methodology in this powder based system is the SLS, selective laser sintering, and MIT has been used the glue based, that they have called the 3D printing, that their product they have called as a 3D printing. So now we are using for each and every methodology with this name because it's a relatively catchy word. Similarly, the lens, the laser engineer net shaping is the another method, promising method in the powder-based additive manufacturing process. But ASTM modern classification of additive manufacturing process has been proposed. It based on the 7 methodologies. So 7 methodologies by which the material will add layer upon layer. So the seven methodologies are photopolymerization process. That means liquid resin has been solidified by photopolymerization process layer after layer. And right hand side column we mentioned the man process or manufacturer developed that one. Second methodology, the sheet lamination process that as name itself says, the thin sheet either made of paper or plastic or even ceramic is used uh, which will be laminated one after another to get the solid object. Third one is the material extrusion process, like fuse deposition modeling. Material has been extruded from the nozzle and it will deposit over the platform layer after layer. Fourth method is the binder jetting principle. Here it is the powder-based additive manufacturing. Metal or polymer or the ceramic, even metal powder is used to adhere by means of a glue or the adhesive. So that is why it is called the binder jetting. So binder will deposit it over the powder bed. So fifth methodology is different from the fourth one. Is the fifth is also powder based fusion. Here laser is used to start the sintering process or to fuse the metal powder to adhere with each other instead of glue. So sixth one is the material jetting. Here directly instead of binder jetting or binder depositing in a droplet form, here material will deposit the liquid material which will deposit and it will cured under the UV control environment. So that is the material jetting principles. So multi-jet or object, these are the product already developed. And the last one is another promising one, the direct energy deposition. Here also powder and laser will use simultaneously to create a metal droplet here to deposit, and it has a lot of flexibility with respect to the previous six methodology. So first I'd like to show you a few promising application of additive manufacturing methodology, and then I'd like to explain the working principle of that. And let us start with this one. So I like to show you some applications of additive manufacturing process. So you can manufacture your own tool. It will also use the artwork. You can create any engineering prototype, architectural prototype for visualization, even cloth design, furniture design, machine component design, either used for the verification purpose or even for the, it is also used in the biomedical sector. So even you can manufacture your own robot by this method. So the possibilities are endless. So next I'd like to show you a few exciting application of additive manufacturing.
Which was never before possible. This new technology can also reduce costs and decrease building times of daily use tools. So let's take a look at the best 3D printed creations. At number 10, the walking gyroscope. Invented back in 1981, the 3D printing world has brought back this really cool toy. This is built in several components and it houses a spinning gyroscope which is geared to a pair of walking feet. You can even build your own since the 3D model can be found on thingiverse.com. So make sure you check my description and click on the link to this 3D toy. That's number 9, a CNC multi-tool machine. Although it's not quite a 3D printer, this CNC machine is mostly made from 3D printed parts and is a lot cheaper than your average machine. It can work with woods, plastics, and even some metals. So I think I'll make sure not to incorporate an AI program.
The component of 3D print CNC machine has been manufactured by additive manufacturing process.
At number 8, the Cortex.
So this is another interesting application. So with this sort of plaster, there is no itching problem, and it is customer specific, custom made.
And then a 3D scan, and then a fully custom 3D cast is printed out. So this is definitely innovative and very beneficial to people who have to deal with an injury. At number 7, the Dodi Kihijoin speaker. With 3D printing on your side, building a complex speaker box becomes fairly easy to do. This 12 speaker array gives off great sound while being exponentially cheaper than some of its commercial counterparts. I expect to see and hear pretty cool 3D printed speaker housings in the near future. At number 6, the Forms in Nature light sculpture. This unique light casts 360-degree shadows onto its surroundings, which gives the illusion of being in a forest. New custom 3D lights are being designed.
So you see, my traditional manufacturing process with this complex thing is impossible to manufacture.
Four-cylinder engine. This does not run on fuel like the real engine. It's actually a replica composed of many 3D printed parts. Built by Eric Harrell, once again you can visit Thingiverse.com and print your own replica engine, but it'll likely take you over 70 hours to print. Every part moves, and it's driven off an electric motor. And if this is not crazy enough, the same creator even built replicas of a 5-speed transmission and a transfer case. So that's pretty crazy. At number 4, the Locomotor's 3D printed car. Most of this car is composed of ABS plastic reinforced with carbon fiber. Its frame, exterior body, and interior features only take about 40 hours to be 3D printed. Its mechanical components, which consist of battery, suspension, and brakes, are not 3D printed but are added on after. It's a fully electric car with a top speed of 50 miles per hour, and it's expected to be released next year. At number 3, a real 3D printed jet engine developed by.
So it's the metal 3D printing is used here.
This new engine proves that 3D printing methods can cut costs and production times. Its creators are hoping to test fly a prototype within 10 months. If everything goes well, commercial certification will be awarded in the next 2 years. 3D metal printing is a fairly new thing, and it will not only improve engine building times for the aviation industry, but also for the automotive and marine sector as well. At number 2, the Protohouse scale model. This project tested the boundaries of large-scale 3D printing and brought forth a very unique nest interlock style type of house. Okay, it might not be a house which everyone would want to live in, but it does.
So that Professor Pal already mentioned the use of additive manufacturing in the building manufacturing and in civil engineering.
At number 1, a 6-story printed apartment building built in China by Wing Sun. This apartment is
So 3D printed building.
Industrial waste, along with quick drying cement. The
Using the recycled material.
building is 10 meters high and 40 meters long. It fabricates components and then everything is put together on site. Steel reinforcement and insulation are then added in.
So in this way, recycled material is used in 3D printing.
Increasing labor costs by 80%. Wing Sun is also.
So I would like to explain some working principle or the of a additive manufacturing process. From there you can see what are the research opportunities. So we like to start with a very simple one, the old one, that is the sheet lamination process or laminated object manufacturing process, which is according to the first way of classification to the solid based RT system, and first commercial system in the name of LOM 1015 developed by the Helices US in the year 1991. But this is not the first additive manufacturing process. This is first additive manufacturing process I will show you next. So material is the solid sheet coated with the heat activated adhesive, that is the thermoplastic adhesive. It is the paper or maybe plastic, composite sheet, ceramic sheet, even nowadays metal sheet is also used. Layer thickness is 0.05 to 0.25 millimeter, and the process is the laser cutting and the lamination by the hot roller compression. Laser type either CO2, and the laser power, it depends, it's 25 to 50 watts. And the basic process is, you know, that physical prototype are produced by the successive bonding of the thin layer of heat activated adhesive coated material or the sheet, then laser cutting of the cross sectional outline according to the cross sectional information after slicing. And then in order to do that, as you know the step, first you have to develop the 3D CAD model that has to be saved in a .htl format. No support structure is required in this case, and it will slice it. Then slicing means cross sectional information will fed to the machine, and according to the cross sectional information, the way the machine will work is like this. So in this particular machine, you just see here So this is your material supply role. So this material supply role, now you pull this material from here, and this is the platform. This is your building platform, and building platform is lowered down and up. It basically CNC control by screw nut mechanism, simple ball screw nut mechanism. It can move the platform can move up and down. Now, initially over the platform on a simple dummy paper is there, so that the platform will be safe. Now, over the dummy paper, this adhesive means thermoactive adhesive your thin sheet coated with the thermo or heat activated adhesive will be take it out from the material supply roll, pull over that, and it will be clipped with the takeoff roll. Now, once this fresh material come, then the roller will move. Roller will move over that particular sheet, and roller is temperature control and pressure control because of the temperature and the pressure that below the glue. In this particular paper, below there is a heat activated glue that will activate, and it will adhere with the previously created dummy layer. Now, according to the first cross-sectional information, for example, if your product will be like this, if your product is say like this, so though it is not drawn engineering drawing, so it is, let us say, so it will cut first according to this is the first layer, this is first layer, and according to geometry, first it will cut this particular boundary, then this boundary, same has been done here. You see, the first this boundary has been cut, then second boundary has been cut. Now, what you have to do? These two boundaries has been cut, and that in order to cut this boundary using the laser, you have to control the laser path in XY plane. So there is a optical devices which is control the XY position of the laser point, and by this it will cut the outer periphery, outer cross-sectional periphery, inner cross-sectional periphery. Once it is over, next this has to be cut rectangular or block you have to cut with the maximum outside of the maximum cross section. So it has some advantage because whenever a platform is lowered down, whole rectangular thing will lower down. It will detach from this particular roll material. Now, after cutting this one, the unwanted portion is inside the unwanted. This portion is the unwanted, along with this one unwanted. This has to be crossed hatch. So crossed hatch having certain advantage when you like to take it out that unwanted portion. If it is crossed hatch previously, then you can easily remove that one. So once the first layer is over, the platform is lowered down equal to one layer thickness. And once the platform is lowered down, whole rectangular thing will lower down along with the platform. And the movement of the platform is controlled by CNC and it by the precise ball screw nut mechanism. So once it is lowered down, it separate this particular thing from the main roll. Now takeoff roll will activate. It will takeoff roll will rotate like this, and because of the unwanted portion will be depositing, or it is rolled here, and the fresh paper will come over the first layer. Once the fresh paper sheet will come, then that time the laminated roller will again roll over that, and because of the temperature and pressure, it will adhere that particular this current layer with the previously cut layer. And according to again second layer cross sectional information, it will cut the cross sectional outer boundary, cross inner boundary, outermost rectangular boundary, and cross has the unwanted portion. So again, this once the second layer is over, platform is lowered down, and this process will continue till topmost layer will come. And if you'll see ultimately this process here, so I like to show you in animated way. The way I mentioned same thing, I like to show you through animation. So this is the XY movement of your laser head. It will control the XY path in XY plane. So this is the roller, this is the sheet, cutting is going on. After roller, then platform will lower down. Once it is over, then again takeoff roll will run and it will collect the unwanted portion of the paper. So in this way, the process will continue, and ultimately what you will get, so you will get this sort of block, and you have to remove the unwanted portion from this block. Sorry. So the block you have to remove this way. So from the block, unwanted portion you have to remove. So though this material, this particular process, there is the wastage of material, and that is why nowadays this particular process is obsolete. But it is a very simple way you can explain the working principle. So that is why I have chosen this example. But nowadays this is obsolete because of the wastage of material. Now, if you see the mechanical point of view, the systems, they are having the laser optics, XY positioning device and motion control, platform, the vertical elevator through the ball screw and nut mechanism, that the lamination system like hot roller, material supply roll, takeoff roll, computer hardware, because CNC, it is basically the control is the computer numerical control. And if you like to see the modern one, it's is slightly different. It looks like our 2D printer.
Convert your 3D CAD designs into three-dimensional rigid plastic models that help you improve the speed, quality, effectiveness, and cost of your design projects. Its lightweight, compact design and quiet operation allows you to position the printer right in your office, even on your desk. The easy-to-use LDU software provides quick, easy setup to begin building your model. Building layer by layer until the model is complete, the Envision LD 3D printer uses proven water-style operation to produce durable, rigid plastic models. Speed of the build is dependent on the size, number, and complexity of the models being built, but most parts can be built in just a few hours. When your model is complete, simply open the door and lift the model from the build area.
So it is the plastic sheet is used in this case.
Removing easy peels.
Here also same thing, there is a wastage of material.
Just pull in the hand of the.
So now I like to tell you the first additive manufacturing in the world that is developed by the Professor Hall, and he also the founder of 3D system, and the machine that you have seen here, this is the first additive manufacturing machine in the world, and that name is stereolithography apparatus, and method is photopolymerization, and it is based on the your resin or liquid resin. So it is a liquid based additive manufacturing process, first commercialized in the year 1988 in 3D system, and material used is the photocurable resin. It may be epoxy resin or acrylate resin, laser type is a helium, cadmium or argon ion, and there is a movable platform. The working principle is similar to previous. There is only one exception is there. So here you just see that vat is full of photocurable resin, And initially this particular platform will be here. Initially it will be at the top at this particular position. Here it will be the term, and this particular platform I already mentioned, its position has been controlled by the CNC and numerical control. And the mechanism you see is the recirculating ball and nut mechanism. And when the platform initially at the top, and there is only thin layer of resin over the platform is exists. It's equal to the one layer thickness according to your STL file, according to your slicing file. Now, according to the first layer cross-sectional information, your laser will control its path. This laser will trace over that particular one thin layer of resin, and its motion has been controlled by, again, there is a servo mirror control is there by which the laser path is to be controlled. Now, in this case, only difference with respect to the previous one, suppose if your cross section is like this, like previous, suppose cross section like this, in this case laser will trace not only this particular outer boundary, cross sectional boundary, and inner cross sectional boundary, it also traces inside, because due to the interaction of the laser and the liquid resin, the resin will start curing by the photopolymerization process. And in order to do that, you have to trace the laser on this cross section. Otherwise, it remain as a liquid resin. So wherever laser will trace the path, there will be a interaction with the laser as well as the resin, and because of that, photopolymerization process start and it will start curing. And that is why laser has to be traced like this way. It has to be traced the complete cross section. Otherwise, wherever it will not trace, that becomes in a liquid state, and it will not create the complete layer. So that's the difference between the previous one and this. Previous one, it is a solid object itself, that is the only boundary, outer boundary, inner boundary cutting was sufficient. But in this case, it has to be traced like this way. Complete cross section has to be traced, so has to be followed, so that there is interaction with the laser beam and the resin, and it will start. So first layer is over. Once the first layer is over, then the platform is lowered down by means of this control system, this mechanism, and it will lower down at such a way that because of the lower down, surrounding your resin will flow over the previously cured layer. And as there is a turbulence during flow, and that is a vapor blade. So vapor blade will quickly distribute that particular fresh layer over the previously cured layer, distribute the resin, liquid resin, thin layer of liquid resin uniformly distribute quickly over the previously cured layer. Next, according to the second layer cross-sectional information, liquid your beam laser will trace the path, and laser power control in such a way that it not only cure the second layer but also creates the bonding between the second layer with the first layer. So this way the second layer will do, and after that again platform is lowered down, and this process will continue. The till topmost layer will come. So tracing, curing, and recoating are the steps that has to be repeated. And you just see this is the machine, which is one of the oldest machine. It was there in the NIT Durgapur, and now it is not in working condition, but it is the one of the oldest machine in India as selective laser sintering, and these are the product developed using that particular machine. So here I like to show you that some videos of the stereolithography method. You just see the big machine. Some pre-processing or the process parameter, the very important thing, the process parameter. So each process, there is a process parameter that has to be set. So these are the stressing of the laser according to the cross-sectional information. might be, and after that platform lower down, and this is the wiping blade. It will basically uniformly distribute the second layer of the liquid resin, again the stressing the path, and this process will continue till top material will come, and after that the platform will move upward direction, so that whatever process has been whatever product has been built, that is not fully cured, it is somewhat 50% strength is there. Now it has to be do the post curing operation under the closed ultraviolet chamber. So whatever product we'll get from the SLA, that strength is 50%, because it is not fully cured, it is partially cured. Now you have to do some post curing operation under the closed UV chamber. So these are the product created using the stereolithography apparatus. So from this you can say the usefulness of this particular methodology. So third methodology I like to explain is the fused deposition modeling, and it is the most popular additive manufacturing process, and based on the material extrusion. The machine is looks like this is the product, and this particular machine is, you can say, it is a purely mechanical. So that is why it is, the cost is very less, very popular in the academic institute in India. It is called as a solid-based RP system. Proprietary process is basically statistics, but proper that your patent already over. Now many companies are manufacturing this one to make it low cost. So material used is the ABS plastic or PLA or any other polyurethane elastomer. A basic process is same as initial process same. First you have to develop the 3D CAD model, save into .stl format. In this case support structure is required. You have to create support structure, then you have to do slicing using proprietary software or any open source software. Now if you see the manufacturing process steps, then it is basically somewhat mechanical. Here the input material is in the form of filament. So input material is the form of a filament of 1.25 millimeter diameter, filament diameter, made of PLA, or it may be made of ABS, and it will fed to the extrusion nozzle or extrusion head, which is temperature control as well as position control. So extrusion head is both temperature control and position control, and filament will fade through the roller. So there are the multiple roller through which filament will fade within the extrusion nozzle. And as there is a continuous flow of filament in this particular nozzle, because of the back pressure, it will create the back pressure inside the nozzle, and nozzle is temperature control. Its temperature has been set in such a way that solid filament becomes semi-solid state. Once it is semi-solid state, and because of the back pressure, it will come out, and that nozzle diameter here is 0.4 millimeter. So very thin layer of the semi-solid material will be deposited. So semi-solid material of 0.4 millimeter diameter is extruded through the precise nozzle, that means nozzle diameter I already mentioned, and deposited in ultra thin layer on this platform. And here let us say the XY control is given in this case. XY control is given in the head, and Z control has been given in the platform. Platform will lower down by screw nut mechanism, whereas that your head will be moved in XY plane by different mechanism, either rack pinion mechanism or the timing belt pulley mechanism, by which you can move that extrusion head. An extrusion head, according to the cross-sectional information, it will deposit material in XY plane. Now, if there is an overhang structure like here, let us say this is the overhang structure, this portion is overhang. If there is overhang structure, then you have to give support material from the bottom, red color, here it is the support material. So many machines, there are the two nozzle, one nozzle for the functional material or the build material or the material for the product. Another nozzle is used to deposit your support material, because you have, once it is over, you have to take it out the support structure. And if it is aqua soluble, then it is very easy to remove. Otherwise you have to use mechanical process to take it out from the object. So it's sometimes difficult, and it will create low surface finish, or surface roughness will be more. So that is why support structure material, if you can use different and it will be easily soluble, then it will be relatively better one. So it has been shown that that is a two filament coil or filament roll, one for build material, another for the support material. Red one is for the support. Now, once it will deposit at the air surrounding the abdomen head is maintained at a temperature below the metal melting point temperature, then exit metal quickly solidify, and it will deposit according to the cross-sectional information. And once one layer is over, then it will the platform will move downward equal to one layer thickness. Then according to the second layer cross-sectional information, the again material will deposit just like a toothpaste. You just see that if you in toothpaste you can create pressure from the back side by your finger, the toothpaste will come out. Similarly here also. And second layer will deposit, and due to the thermal fusion, it will create the bonding between the second layer with the first layer. So here I like to show you that the process through animation. So if you use deposition modeling, it will be more clear if you see this animation.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer on a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material on the preceding
So
layer.
here the white color on the support material. So white color support material, and if you see the structure of the support, it make a honeycomb structure so that you can easily remove that one.
Building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts, including hand sanding, assembly.
So post-curing operation has been shown here. Now sometimes we are jokingly called this process is similar to our jalebi making machine. The way we are making our jalebi, that is same concept. So here the cloth one is basically nozzle, there is a hole, and we are creating the back pressure by finger, and semi-solid liquid will come out, and according to your XY movement of hand, the different geometry or different cross section you will get. So same concept used in your FDM. Now, the important thing for the any manufacturing process is the process parameters. So process parameter is very important, and optimizing the process parameter is also important to make it sustainable. So the major process parameter for the FDM process is the material viscosity, material flexural modulus, deposition speed, volumetric flow rate, tip diameter, envelope, temperature, horizontal width of the extruded material. So these are the process parameter, and this is the product developed by the FDM process. So next, the fourth methodology I like to explain here, the powder bed fusion methodology, and the process, the very first process, the selective laser sintering SLS process. So it is a very promising one. It is the powder based system first commercialized by DTM in USA, and material used that time in the polycarbonate, nylon, wax, glass filled nylon, and the powder coated metal and ceramic. Process is sintering. Sintering, as you know, is the process by which the powder are caused to adhere together by application of the heat. Heat may be given by the laser here. And sintering occurs when the particle viscosity drops due to the increase in temperature and allows surface tension to overcome the viscosity. And in this particular process, it fusing the powdered thermoplastic material and heat is generated by the laser. So the CO2 laser and process is same, but in this case one advantage is no support structure is required. So one of the major advantage of the selective laser sintering, there is no extra support structure is required, so material wastage is minimum and even a much lesser than, and powder also reusable. So if you see, the process is similar to SLA. Similar to SLA, only difference is instead of a resin, you have to there you have to, resin has to be sprayed over the layer, over the platform. Here it is the powder. So it starts with a thin layer of the heat fused preheated powder, because it is the platform you just see here. So this is the platform. Over the powder will be there, powder delivery system, powder will be stored with the preheated, and this one the build platform. Initially the platform build platform is here, and over which powder has been sprayed by means of a roller. Now as the one layer of powder has been sprayed, and it is now similar to your SLA process, the laser is traced the path, and this, in this case also, path means it's not only the outer boundary, it also traces the inside, because due to the interaction of the laser and the powder will fuse and adhere with each other. So that full cross-sectional tracing is required. So once the first layer is over, then this platform is lowered down, mechanism is same, equal to the one layer thickness, and this delivery platform will move upward direction, and the heap of this particular powder will spread by means of roller. It may be the single delivery system or multiple or two delivery system, like here. It is the one delivery system this side, another delivery system this side. It will save the time. With one time roller will move from this direction, on a second then a roller will move in this direction, it will save a lot of time. So once the second layer is sprayed, after lower down that particular build platform, now again according to the second layer cross-sectional information, laser will trace the path, and laser power is controlled such a way it not only fuse, not only make adhere of the second layer powder, it also create the bonding between the second layer with the first layer, and this process will continue till topmost layer will come. So it's only difference from the SLA and SLS is, in SLA there is a liquid resin, in this case it is the metal powder. Another difference is, as the free powder is act as a support, here you see overhang portion, free powder act as a support, so no such extra support structure has to be designed, and the powder is also reusable. So this is the major advantage, no support structure, so that is a no wastage material for the support structure, and powder is also sometimes reusable. So that is why this is one of the promising method. Powder based additive manufacturing is more promising than others. So here I like to show the DMLS. So the
metal laser sinter, also known as
laser sintering, here this is the same component has to be manufactured. This one is the interaction with the powder with the laser, and it is fused.
Utilizes a variety of metal and alloy materials, such as stainless steel, cobalt chrome, and Inconel, to create strong, durable parts and prototypes. TMLS is an excellent choice for functional metal prototypes, high-temperature applications, and end-use parts. The TMLS process begins in the same fashion as other layer additive manufacturing technologies. A program takes 3D CAD data.
So 3D CAD data, once you slice it, you see this type of cross-sectional information will be stored into the CAD database, and that will fed to the machine.
TMLS machine exactly where to sinter the metal material. Data then transferred to the TMLS equipment. A recoder assembly.
So this is again spreading the powder, then laser tracing, again spreading the powder, laser tracing, and the process will continue.
The built material, heating and fusing the material. Once a single layer is complete, the base plate is lowered just enough to make room for the next layer. More material is raised from the cartridge and recoated on the previously sintered layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength.
So unused powder can be reused.
The completed part is then removed from the base layer and treated with an age-hardening process to further harden the part. Any support structures are also removed at this time. With numerous surface treatment and hand polishing options available through service providers such as Solid Concepts.
So these are the components that be manufactured by selective laser sintering process. The fifth method I like to explain here is the binder jetting principle. Here also the difference between the previous one and this one, both are powder based, but here instead of laser you're using the glue, depositing the glue. So it is developed by the MIT and their product has been named as your 3D printing. And nowadays all printer were considered a 3D printer, but actual name coined by MIT Boston. And that has been licensed, that considered licensed to many companies. And the process, if you see, this is the machine and the process, instead of laser, we are depositing the glue. Other thing is remains same, spreading the powder over the bed. Then according to the cross-sectional information, the glue will deposit that particular cross-section and it will adhere the material. And once it is one layer is over, then again it lowered down the platform. Second layer powder will spread and then depositing the glue from the tiny nozzle. So nozzle used here is same as the inkjet printing nozzle. Instead of injecting ink, it is injecting the glue. So if you see that the first machine, that Jet Corp has been commercialized initially, now has been taken over by 3D system. So they see the printer head only used here. The general inkjet printing head is used in this case. XY movement, powder bed, white color is the powder bed. So this sort of printing, that means the binder jetting principle is nowadays promising in case of a biomedical engineering, and in also in casting. I like to show some example. Is a very promising one. Is the cold powder based additive manufacturing process. Is the cold powder based additive manufacturing process. So in this case also no support structure is required. That is where it is beneficial. So wastage of material is less. Same if you like to manufacture by traditional manufacturing process or any other additive manufacturing process, if support structure is required, then there is a wastage of natural resources. But in this case, wastage is less. So now I like to show you one example of, based on this principle in the mechanical engineering, casting is very important. Now that you can say the patternless casting process. You can treat this as a patternless casting process, and it is huge saving of the natural resources. You know, the pattern has been manufactured by the wood, and if you can eliminate that particular process, pattern making, then it is a huge advantage in respect of saving the natural resources. So here multiple parts has been manufactured at a time. Multiple mold has been manufactured at a time. Because machine is big machine. The print process starts. See, here it is depositing the glue. This is the head. This is the print head, consists of a nozzle, and glue will be deposited over the sand bed. Sand powder has been sprayed here. So this has been according to the cross-sectional information. Now it is spreading the sand powder over previously glued layer. Spreading of sand powder. Now again, according to the second layer cross-sectional information, the glued are deposited from the tiny nozzle. See the some colored deviation, that is glued actually. Now once your process is over, layer after layer adding the glue, then unwanted sand powder has been collected by vacuum. Now see, this is your mold. For casting process, mold has been printed. Printed mold, this one, sand mold, printed sand mold. So from post curing operation has to be carried out. So in this way, that mold, sand mold has been printed. Now pouring the material and casting. So next methodology is the material jetting. So it's the same as the binder jetting, but except here no powder bed. The material by which the product has been manufactured, that is directly jetting over the platform, and the platform is under UV control. Once it will deposit, because of the UV control, it will solidify. The second layer will deposit through the tiny nozzle, and this way it will continue, and the polyjet is example of that, and is developed by the strategist. So last one is the direct energy deposition. In this case, it's different is from the your powder bed fusion. The difference here, it's a specially designed nozzle where from the center laser will pass, and the concentric circular circular slot is there from which the laser, your powder will come out, and at the tip of this nozzle, the laser will meet with the powder, and because of the interaction, it will fuse and it will deposit the material, the molten or the droplet form material will deposit over the platform, or it can also use for repair purpose, and as it is not depends on the powder bed. If you can attach this sort of things over the robotic things, over the manipulator, then it has a control in X, Y, Z, as well as orientation about X, about Y, and about Z. 6 degrees up to this you can achieve. So this is the schematic diagram. The centrally, this is the laser beam, and you just see from here that the powder, the nozzle is specially designed. From the powder feed here, and at the tip, the laser as well as the powder will made, and it will fuse and it will deposit. So the example I like to show you here, the robot is used in 3D printing also. The principle of from, though it is a different deposition, not the DMD, but same concept is used for DMD also. Robotic 3D printing, these are the example of that. The big object, if you like to manufacture, you can instead of even that is called Gantir kind of robot, and here it is the articulated robot is used for 3D printing. So this is another new area of additive manufacturing and the robotic technology, and both are the element of the industry 4.0. Now just see which way it could be sustainable. This, for example, any new product development, what you can do, suppose the researcher will develop the concept of this person, let us say the innovative turbine blade, the complex shape. What you have to do that based on the design, the carpenter or the pattern maker will make the pattern. The traditional manufacturing process will do like this way. The pattern maker will make the pattern, then mold maker based on the wooden pattern, mold will create. So both case human skill is required, and then casting, then finishing operation to get this one. And in this particular process, you see the wastage. Pattern making, the natural resource wastage, mold making, the sand, this also is natural resource wastage. Because once you'll get, and after casting, there are runner, riser, you have to cut out, make it finish, again the material is wastage. So, but instead of that, if your material science and the additive manufacturing advance properly, then there are two more routes. So one route I have already shown, that directly you can print the mold by the binder jetting principle, that the previous sand mold, 3D printed sand mold. Then also in that particular route, you can at least save the material used for the pattern, time, as well as the material used for the pattern, that the time and cost both will save. If you, this is the first route, directly print the mold, then casting. Second route, instead of creating the pattern and molding, directly you can print this particular cross section. If your material permits, strength permit, then only. So there is a limitation. If it is permits, then you can create directly this one. And obviously, if it is the mass production, that might not be economical. But if it is the customized production, then its requirement is a little bit less. Then till date, whatever technology is there, it is the cost effective also. But in near future might be the technology will so advanced will be, and because of that, cost also drastically reduce. Now somewhat monopoly business is going on, and because of that, the a lot of value addition is there, and that is why that machine is costly. Ultimately, the product cost is high. But maybe in near future, it machine cost will move downward direction, and at the same time product cost will be less, and material flexibility or material advancement and material adhesion technology will improve, so that we can get the strength also. So if you could directly print this complex shape, then it will save lot of time, lot of material for other purpose like pattern making and mold making. So that respect, as you know, sustainable manufacturing have that objective. It should be less wastage and the less utilization or the optimal utilization of the natural resources. Both will be possible in this case. So application I already mentioned. I like to skip that particular part. Few examples like G has taken over by many additive manufacturing companies, and more specifically the metal additive manufacturing companies to manufacture their product. And that is why in the developed country you can see most of the aircraft giant, they have take over the many additive manufacturing process, so the technology will not disclose to other. They are using this technology to make the aircraft more lighter, aircraft component is more lighter. And if you can create the complex shape complex means that I will tell the in respect of additive manufacturing, because honeycomb structure you can create in additive manufacturing. Shape complexity is not at all a problem in additive manufacturing because you're converting 2D into 2D. So the honeycomb structure or the stiff using the lot of stiffener in the structure, if you can like to manufacture by traditional manufacturing process, it is next to impossible. But additive manufacturing process easily you can manufacture. And the aircraft company are taking that advantage, and there are the new domain has come up that is called the design for additive manufacturing, and based on that they are creating the relatively much lesser weight aircraft component. And if your aircraft weight will be less, then the fuel economy will improve, and ultimately you are saving natural resources. So I like to show this example. You can understand how you can make a lightweight to make inside honeycomb structure or any other lattice structure, either honeycomb structure or any other lattice structure. So though it is a 3D printed wooden gate for the wood dust filament, but same concept design you can use for engineering product also to make it lighter, but keeping the strength aspect is same, strength and the stiffness aspect same. You can make it lighter. See that inside is the honeycomb structure. Or some cases you can use the lattice structure also to make it more lighter. So this is delta type additive manufacturing machine. It's similar to a parallel manipulator or parallel robot. So I like to skip the 3D printing. Is also used in jewelries for pattern making. It is also used in food industries. But another promising area of additive manufacturing is the bioprinting or the application of additive manufacturing in biomedical sector, where the mass customization is essential, because it is patient specific implant development. If you can try to manufacture by traditional manufacturing route, its cost will be high because of the separate tool and die for the different patient. But if you can use additive manufacturing, then it will make a customer or the patient specific implant with taking their image or the MRI image of that particular bone or any other part or any other organ of the human being, and it can create by the additive manufacturing process a huge impact in this particular area also. Now here I like to show you one of my area of research interest is additive manufacturing in the micro and nano scale, and there you can understand what is the future scope. So additive manufacturing process is sorry, just a minute. So micro additive manufacturing, these are the different micro additive manufacturing process. So macro additive manufacturing process also used in micro domain. So there are some inkjet based additive manufacturing process which is used for even micro and nano level. So these are the different nano additive manufacturing process like the deep pen nanolithography, self-assembly. But here I like to show some application like your functional tattoo in biomedical, where you can use micro level additive manufacturing process using functional material, which is also costly sometimes. Now here one micro additive manufacturing process, the inkjet printing, which is used nowadays for the MEMS sensor development, because which is also used in order to implement industry 4.0 sensor technology is very important, along with the actuator, smart actuator and smart sensor, and that might be the MEMS based, and that manufacturing by additive manufacturing, because it is save lot of costly material. The sensors and actuators are made of a relatively costly material, and if you can use the traditional MEMS manufacturing process, it will be the somewhat subtractive. There is a wastage of material, and that is why in the developed country they are switch over to the additive manufacturing process for the MEMS device manufacturing, for the your micro sensor development, display device fabrication, TFT fabrication. So they are switch over to the additive micro additive manufacturing process, mostly in USA, in your Korea, Japan. They are extensively used the additive manufacturing process, and more specifically the inkjet printing process for this particular flexible electronics and sensor this area. So here you just see the inkjet printing process in micro level. Also there are the for three basic principle. One is thermal jetting. You just see here the coil is used. It will form because of the electricity. It will heat it up and it will form the back pressure, and because of that droplet will create, and it will push from the it come out from the nozzle. Or it can be piezoelectric based, where again the piezoelectric material is deformed. If it is under the potential difference, then to use that one to create back pressure to create the droplet which is come out from the nozzle by pushing the in. So, but in this process, it's if you like to make it the nano level droplet, then because of the scaling effect, the back pressure requirement will be huge. So, nano level droplet creating using this pushing method is very difficult, because the pressure requirement is more because of the scaling effect. So it is not unable to print sub-micron level droplet size, and proper placement of the droplet due to the vibration of the piezoelectric actuator is also difficult. Nozzle will clog due to the ink viscosity. Nozzle design for the high resolution is very difficult, because you have to create the nozzle diameter also in nano level. So it is very difficult, because whatever droplets come out from the nozzle, the diameter of the droplet is higher than the nozzle diameter. So that is why if you like to create some micron level of droplet size, your that nozzle output diameter is lesser than that. So then only you can create that nozzle, because the droplet size is high. If it is push it, then the droplet size is higher, droplet diameter is higher than the nozzle diameter. And it may be some clogging problem might be there, and that is why that electrohydrodynamic principle is used in inkjetting. So here we are creating the potential difference between the nozzle and the substrate platform. And because of this potential difference, it will pull the material in, and it will form the Taylor cone here. And at the end of the Taylor cone, droplet is formed. Droplet will not form from the nozzle end. Rather, because of the electric field, it will pull your ink will pull, and because of this pulling, there are some fluid mechanics phenomena there. Because of that, Taylor cone will form. At the end of the Taylor cone, the droplet will form, and because of that, as the Taylor cone is the liquid part, at the end of the droplet will form, and that is why droplet size is much lesser than this inkjet or the nozzle size. So that is because of the external electric field has been used, and that is the one of the promising area in the micro and nano additive manufacturing process, electrohydrogen ingot printing process. And these are the setup we have developed under the DST project, and in the collaborative project between NIT Durgapur and CSR CMRI Durgapur. And in this particular DST sponsored project, we have developed the experimental setup of the electrohydrogen ingot. Now, what are the challenges here for the micro additive manufacturing process? Challenges is to micro and nano scale 3D structure at a large scale with greater accuracy and high resolution and low cost. The very important low cost manufacturing, still it is still some research has to be carried out to make it low, and material limitation is also there. Another area I like to tell you just after, machine condition monitoring is considered as one of the important area where the people can do the research to ensure the product quality and reduce the manufacturing and maintenance cost, because ultimately in order to make your manufacturing process sustainable, cost is also important, very important, along with the less energy consumption, less wastage of material, and your less use of the natural resource along with that, and obviously cost will be less, keeping product quality as possible. So maintenance cost is also has to be reduced, and that is possible by using the proper online condition monitoring, and there IoT will come into the picture. So as most of the micro and additive manufacturing machine are not equipped with the real-time sensor-based monitoring and feedback control system, so that has to be a open research area. So material limitation is there. Till date, material used is the polymer, metal, composite, and ceramic. So as you know that material till date there is a limitation in the material in additive manufacturing, and research is going on that particular area. Different metallic powder has been used. These are the options. Polymer is extensively used. ABS, PLA, nylon, polyurethane rubber also used. Some ceramic material nowadays used either in a powder form or in a slurry form or even in a sheet form. Metal additive manufacturing is the laser-based metal additive manufacturing is nowadays developed by the many companies. Biocompatible material is used for the biomedical applications, so but still a long way up to move to do that particular get the proper strength as well as the surface finish through additive manufacturing process. So these are the research area where the researcher can focus. Functionally graded material, another important, that is possible by additive manufacturing process very easily. So that is another promising area in additive manufacturing process, to deposit material to make it functionally graded material. That means material property change from layer to layer. So that unique capability can be used not only in macro level, in micro and nano level also it is possible. So that it is may not be possible by the traditional manufacturing process. And as you mentioned, functional geometric complexity is not at all a problem in case of additive manufacturing process. So that is the major advantage with respect to your traditional manufacturing process. So that is the novel one. Geometrical complexity is not at all a problem. It is easily available, and it will be more effective when your geometry is complex. The capability of optimized geometry and creating the lightweight component that reduce the material consumption, manufacturing, and energy consumption in use will be the prime factor in order to make the process sustainable. And there, that additive manufacturing beat any of the manufacturing process in respect of material consumption and ultimately the weight. Because you know that you can create the lattice structure, you can create the honeycomb structure to make it more strength and more stiffness. As you know from your strength of material, if you can distribute the material in the furthest distance from your neutral axis, it will be be more strength as well as more stiffness, and that is possible by topological optimization of your product, and that can be manufactured. Topologically optimized design can be easily manufactured by additive manufacturing process, but that might be difficult in case of a traditional manufacturing process. But obviously there are some limitation in additive manufacturing process, but this is the advantage, and from that point of view you can say if you can improve the material property and strength, it will be sustainable in the long run. Small batches of the customized product are economically or attractive relative to the traditional mass production process. The customized mass customization is possible instead of mass manufacturing. So the additive nature of the process give material saving that I have mentioned already. In case of a powder base, there are a lot of saving material because there is no support structure, nothing, and powder will be reusable. So wastage will be less. And that is comply with another characteristics of the sustainable manufacturing. And the direct production from the CAD model, because of that, no need for the tooling and the mold is required. So design in the form of digital file can easily be shared and facilitated, and modification and customization. Moreover, inventory will be less. You can send the digital data to across the globe, and the local using local facility they can manufacture, and that will drastically reduce the inventory and the transport. If you can reduce that transport thing, then you know the 3% of the world carbon dioxide emission is from the transport, the container ship transport. If you can reduce that thing, that is the massive impact in respect of the environment aspect. So that is another advantage of indirect advantage of additive manufacturing process. And I already mentioned inventory waste reduction due to the ability to create a spare part on demand. But challenges of the additive manufacturing, the material option still today it is limited. A lot of research has to be done to get the proper strength, accuracy, and finish. Another is the basic surface finish. Now another is online condition monitoring. Another research area. Metrology of additive manufacturing process is the big area for the research. Design for additive manufacturing is the promising area in the product design. So because design philosophy will change drastically because of the additive manufacturing process. Another is the understanding of the science of adhesion of the material is important, and because if you can, then lot of hybrid methodology, hybrid additive manufacturing method will become up if you can understand properly the science behind the adhesion of the material. Then you can easily do the hybrid additive manufacturing process. And obviously the optimization of the process parameter is always important for any manufacturing process, and it is additive manufacturing process parameter optimization is not exception. But through the process parameter optimization, we can get the better strength, accuracy, finish, less wastage, high productivity. All these issues is there. And the speed also increase, and cost can be reduced by selecting the suitable process parameters. So, and if you can do this one, then it make it more sustainable in near future. So that I already mentioned this one. So I like to take a few 5-10 minutes to say sharing that future research area. Future research area I like to point out here: design for additive manufacturing, one area. Another is the online intelligent condition monitoring of additive manufacturing system, design and development of hybrid additive manufacturing technologies, synthesis of material for additive manufacturing, process modeling and optimization for additive manufacturing, and so on. So design for additive manufacturing is a very promising area. You know that see the lattice structure has been designed inside to make it much strength, much stiffness, but weight is less. So the case study I like to show you here is, say for example here, that the seat belt, the clamp that you like to use in the aircraft, instead of the metal, if you can manufacture the composite material, and in 3D printing, if you design is like this, then you see the consolidating the number of component, 8 component into the one part. because the geometric complexity is not at all a problem in additive manufacturing. So that only it becomes 40% lighter and even 20% stronger if you use the properly the composite material. So this 3D printed set belt bracket is one concept I like to show you in respect of the design for additive manufacturing that will reduce the weight, and because of that, ultimately, the objective of any aircraft component to reduce the weight so that your fuel economy will improve, and ultimately that additive design freedom enables the carbon footprint reduction. So that's the most important thing with respect to the environment aspect, and in order to make manufacturing system sustainable in long run. Similarly, I have shown in the automobile sector also, you can see if you can using the topology optimization concept in design, you can make it so lighter structure so that fuel economy will improve. Again, it will enable the carbon footprint reduction. So this example already shown by Mr. Mukesh in yesterday afternoon session, that HP is the case study has been shown 95% carbon footprint reduction because of the reduction of the weight from 355 gram to 23 gram. So in respect of the second research topics, like online intelligent condition monitoring of the additive manufacturing system, I like to share this particular paper where in respect of IoT, as you know, this is the excellent area that sitting in home, using your apps, using your IoT, you can control your machine, you monitor your additive manufacturing system. And researcher is working in this particular area, IoT-based solution for control and monitoring of additive manufacturing process. This is another important area. Third area that where we are working in the process modeling and optimization for additive manufacturing. As you know that any manufacturing process you can model by multi-physics concept, or it may be data-driven statistical modeling, or nowadays can use different computational intelligence or soft computing tools for modeling that additive manufacturing process, or it may be the hybridization of these processes. So obviously, for the multi-physics processes, you have to use the law of physics, where the finite element method, computational fluid dynamics will come into the picture, along with the material property. And next, second one, data-driven. Here, exhaustive experimentation has to be carried out. Sometimes it is costly affairs, but some cases at least you can do by this particular process, and these are the modern. It is also data driven computational intelligence tools, is also data driven modeling technique. One such work we have done little bit using the artificial intake, both statistical method as well as the computational intelligence tools. For the FDM process, these are the input process parameter we have chosen, and this is the output to response that we like to relate, that input output mapping. So these are the input parameters in respect of fused diffusion modeling, like layer thickness, air gap, angle, orientation, width, and number of contour. And we have tried to find out build the relationship between the input parameter and the output parameter, that is called the forward mapping. That you can do by statistical method or by the soft computing or computational intelligence based method. But another thing is more important practice, that in order to get this particular output, what should be the input? What should be the input setting? The reverse problem or the inverse problem. So then forward mapping, we have used different neural networks method and adaptive neurophagy inference system. But the important thing is this one, backward mapping. So in order to get this output parameter, what should be the input setting? So that for that modeling, that particular modeling process or mapping process, the computational intelligence tool will be more effective, and that we have carried out using the adaptive neurophagy inference system. So this I like to skip. This is the architecture of adaptive neurophagy inference system and the challenges I already mentioned. Now I like to conclude here in respect of the sustainability issues. If you see the global additive manufacturing usage or the development, you can see from 2009 to 2020, it is, you can say, exponentially increasing. And because of the advantage that I mentioned number of times, so that is why additive manufacturing in the coming future, it drives the sustainable manufacturing. But lot of research, lot of innovation is required in many aspects of the additive manufacturing to make it more sustainable in near future. And those who are interested to see the work on the sustainable additive manufacturing, I referred the paper written by the professor in NIT Trichy. So I can review. So he has reviewed the state of the paper in respect of sustainable additive manufacturing, then societal aspect, environmental aspect like energy consumption point of view, design optimization point of view, so that he has been well documented through this review paper. I like to share you with this, those who are more interested in this particular area. Okay, thank you for your kind attention. And now, if you have any query, please let me know. Thank you. Okay, if anyone have any query, I also not check the chat box.
Yes, sir. Thank you for this informative and excellent presentation. There are a few queries from the participant side. One is in sustainable manufacturing towards Industry 4.0, what is sustainable refers to? Means how sustainable it guides it towards Industry 4.0.
How?
What is sustainable refer to?
Sustainable means here, if any manufacturing process, if you can preserve or you can save the natural resources, then it's through the less wastage of material, less consumption of electricity, and ultimately it will save the cost. The product cost will be less, and it is also environment friendly. We are not if the emission is less, say, then the carbon footprint will be less. So ultimately, the three factors I already mentioned is the societal, environmental. These are the factor on which your this characteristics will say that whether it will be sustainable or not. A particular manufacturing process will be sustainable or not. That depends on the three main pillars. Okay, that whether it is the economic, whether the societal point of view, it will be safe, reliable, and environment point of view, there will be also less use of resources and less wastage. So in societal point of view, if it is safe from the human being operators point of view, economical point of view, the cost is less, it is affordable, then this feature, if it is there, you can tell this will be sustainable in future. And that is the three main pillar in respect of sustainability or sustainability in manufacturing process point of view. So is it okay or?
Yes, sir. Yes, sir. One more query is there. In classification of AM processes among 7 methodologies, which one you will suggest to be the cost effective?
Actually, cost effective in the sense, if you consider the Indian's perspective, we are not the manufacturer of the machines. It is very unfortunate that we are not giving attention to manufacture that machine. We are trying to import that machine. Now, whenever you like to import the machine, that it's a monopoly business sometimes. Most of the times the company are doing the monopoly business. And also, though it is the research work, they have spent a lot of money also, but somewhat it's a monopoly business and machine cost is huge if in the Indian context. And because of that, product cost will increase. But if you can develop our own machine, own product, own material, then it will be cost effective. In the powder based, I think one of the promising is the powder based additive manufacturing process. Either it is a selective laser sintering way, or it is the binder jetting, or DMD. Whatever may be the case, the powder based is the most promising one. For the most of the application, powder based additive manufacturing is the promising one. But along with the, you can say, the FDM process also for the composite material. FDM for the composite material, not for the plastic. It is saturated. It is, so composite material. If you can material you can use using the fuse deposition modeling process, then it will serve lot of purpose. Now the question is the which one is the cost effective. That depends on which particular means machine we can manufacture indigenously. But promising one is the powder based. Obviously, powder based, anyone, either laser based or binder based, because it has a different domain of application. Application areas is different. If it is the cold powder based additive manufacturing, is their domain is different from, might be different from the laser based your powder additive manufacturing process. But only it is now not cost effective in Indian perspective, because we have to import that machine and it is huge cost they are charging. And also the material, also another issues. Material we have to develop, or we have to do research on material and material adhesion in our own. If you can really depend on the company which is in the developed country, they are telling the proprietary material. They are basically by name of the proprietary material, they are charging huge amount of money for the material also. But if we can develop our own material and own machine, then I think a powder based method which is most applicable, and it will be the cost effective in near future, because the material wastage is very less also. Is it
Hello.
okay? Hello.
Sir, what are the challenges and future of FDM process?
A fuse deposition modeling.
Yes, sir.
Fuse deposition modeling, surface roughness is not good. Strength also not good, because of the bonding between the two layers. There are sometimes problems. So delaminating has been taking place, and surface roughness is also poor. Poor means very poor. Now FDM process has to be improved. For example, one methodology is trying, we have also thought of, but after that we have have seen that some developed country, they are also trying that nozzle diameter till now is 0.4 millimeter, the output nozzle diameter. Using that nozzle, if you can that output material, if you can make it much thinner, even a certain micron. So instead of 0.4 millimeter, if it is a 0.01 millimeter, and that then its strength will increase, because of that thin layer will deposit. So electrohydrodynamic principle is also used along with the FDM. So that is another research area, whether we can use any sort of that kind of thing, electrohydrodynamic principle, or external say external your energy, or external electric energy can provide to make it much thinner deposition. And but still some hybridization can be utilized to make FDM product is much more strength than previous, because there are the company called Markforged. They are using the FDM principle for the composite printing, composite material printing, and their quality also good, and as it is the composite material, strength is not at all a issue. So a lot of improvement is possible because they did some improvement over that. It's not like our traditional FDM made of PLA and ABS. They have used the composite material, and I think FDM and FDM, another advantage is there. It is a low cost because you see in FDM most of the components of the machine are mechanical in nature. There is no laser, so only heating and roller feeding. So somewhat it is more mechanical oriented product, and cost is also less, and that is why FDM is popular also because of running cost is less, product cost is also less, but limitation is the surface finish that has to be improved either by using innovative post processing, or sometimes some hybrid processing. Over the FDM you have to include certain thing so that it will get the better surface finish. So that is one might be on research area to make it some hybridization with the surface finishing process. So anything else?
Which metal will be the best for LS method having good strength?
LS method means?
Himanshu?
Laser sintering.
Yes, sir. Yes. Laser sintering.
Yes.
No, laser sintering. Which method is best? It's not. It is basically
Which method?
for your product. Which material you like to recommend? Whether that is possible by the laser sintering process or not, that is the issue. Because material will, according to your design, according to your analysis, you have to recommend, you have to choose the material 1, material 2, material 3. And now we have to see whether by laser sintering process we can achieve that strength or not. Because it is still means it is in research stage, and newer material is using in the any of the additive manufacturing process, whether it is a laser assisted additive manufacturing process or FDM process. So continuous research is going on, and in the coming 20 years also the research will carried out on that particular manufacturing process. The advantage I already mentioned, geometric complexity is not at all a problem. So that is why through design to topology optimization, you can any complex separate design you can implement effectively. So that is why material research is a big issue, and material addition is also issue. The which method, which process parameter you control so that it can add material effectively and get the proper strength. Hello?
Yes, sir. Any other query? Participants, you can unmute yourself and ask. Sir, one research scholar, she is asking, she is working using FGM, functionally graded material. Can she produce
Yes.
material by 3D printing?
Functionally graded material is easily produced by the additive manufacturing process. Even you can multi-nozzle FDM process using the multi-nozzle FDM. So you can create the functionally graded material. But for that, multiple nozzle is required, and also there are the material science research is required because it should be properly or metallurgically bond between the two layers. No, otherwise delamination will taking place. But by using the multi-nozzle FDM process, you can create the functionally graded material. Another is if it is a not macro level, if it is a relatively micro level, then inkjet based method also can be useful to create the functionally graded material. But obviously that ink preparation is possible or not using that material will be the issue. But by using this method, you can create functional graded material, both by multi-nozzle FDM and as well as the multi-nozzle inkjet printing system.
Yes, sir. Thank you. Participants, I think we can conclude now. I request our HOD, Dr. Kamal Pal, sir, to thank sir for his valuable and very nicely articulated presentation. Please, sir.
Thank you, Professor Roy. Within
you.
2 hours lectures, you have elaborately most of the issues related to Industry 4 and sustainable manufacturing. We are very thankful that within very short period of time, you have responded our invitation. Thank you, sir.
Okay, thank you, Dr. Gopal. So, thank you, all of you, for your kind question.
Brother,
Okay, bye.
so thank you, sir.
Okay, and the material I will send to your mail, that
Yes, sir,
presentation
please.
material slide.
Yes, sir.
So
Students
you
are
can
asking
circulate
for
among the
that.
participants.
Students are asking for that. So you can send it to us.
Hello?
Hello, sir.
Tell me.
Sir, the participants are asking for the presentation.
Presentation material, I will send Dr. Kamal Pal email ID, so he can circulate among the
Will
participants.
circulate among the participants. Yes, sir.
Thank you, sir.
Thank you, sir.
Okay, thank you.
Participants will start the next session at 3 p.m. So please be online prior to 20 minutes. Thank you.